Welcome, everyone. I'm Lori McCauley, Provost and Executive Vice President for Academic Affairs. It's my honor to welcome you all this afternoon. And I have to say, I had a smile when I looked at my event briefing for this because it read, Spring Distinguished University Professorship. And I thought, it is spring. It feels that way outside compared to last week, right? But also makes me smile because this is one of my all-time favorite events, really celebrating distinguished colleagues and hearing from them. It's a great honor, and I know all of you in the room and joining us online will also appreciate today's event. The Distinguished University Professorship Lectures constitute one of our campus's signature academic events. Each year, we receive memorable and enlightening insights into cutting-edge scholarship and the lives of those behind it. First, let me thank Michael Solomon, the Bernard J. Lucci Professor of Chemical Engineering, and our Vice Provost for Academic Affairs and Dean of the Rackham Graduate School for serving as my partner and moderator in today's event. So thank you. I'd also like to extend our deepest gratitude to our three distinguished awardees for presenting us with their lectures today. Distinguished University Professors Mark J. Kushner, Robert Sellers, and Conwell Wang. We are so looking forward to hearing from you. These three members of our faculty are renowned for insights about matter and energy, mechanical engineering, and the essence of the human experience. The respective disciplines of these professors may be disparate, but they share much in common. Each is animated by relentless curiosity. The scholarship of each has defined their fields, and they share our highest academic distinction, the title of Distinguished University Professor. Each of them has also demonstrated a commitment to education and societal impact throughout their careers. In doing so, they've created enduring projects, inventions, methods of research, and developed many scholars who follow in their footsteps. Together, they embody the best of the academy. Professors, you will forever be to our credit, and our campus, our students, and our society are fortunate to have you. Thank you, and congratulations again. And with that, it is my great pleasure to introduce our first awardee, Dr. Mark J. Kushner, the William P. Alice Distinguished University Professor, and George I. Haddad, Professor of Electrical Engineering and Computer Science in the College of Engineering. Professor Kushner is internationally recognized as the preeminent leader in the science and technology of low-temperature plasmas, or LTPs. He has achieved transformative impact through his founding and direction of the Michigan Institute for Plasma Science and Engineering. The major theme of his research focuses on the fundamental understanding and applications of low-temperature plasmas from national defense systems to semiconductor manufacturing and sustainable energy solutions. Along with members of his laboratory, Professor Kushner pioneered the development of computational methods for plasma-based directed energy systems and was the first to adapt these methods to plasma-based material synthesis for solar cells. His groundbreaking modeling platforms are now utilized by major semiconductor chip manufacturers and plasma equipment suppliers worldwide. Professor Kushner has mentored 45 PhD students, maintaining a strong commitment to diversity, with women consistently representing over 50% of his research group in a field where they typically comprise less than 15%. Professor Kushner has received nearly every major award in his field and is a member of the National Academy of Engineering. His work centers on understanding and harnessing plasmas, which constitute 99.9% of the visible universe and are critical to technologies ranging from biomedical applications and water purification to space propulsion and fusion energy. In his presentation, Dr. Kushner will share an overview of the University of Michigan's internationally leading accomplishments and capabilities in plasma science and engineering. Professor Kushner, please.
Thank you. Thank you for that kind introduction. And I'm a little bit unclear on the selection process for the professorships. I'd like to thank everybody who was part of that process, and particularly my former students and postdocs who did the work that I'm being acknowledged for today. In today's presentation, I'd like to give an overview of the research that's performed here at the University of Michigan in the field of plasma science and engineering. To start that, I'm sorry, I have to take you back to high school chemistry. If you remember in your chemistry classes in high school, you were told that there are three phases of matter. You start with a solid, you add some heat, you make a liquid, ice goes to water, you add a little bit more heat, the water goes to steam. Well, that's not quite the story. There is, in fact, a fourth state of matter, and we call that fourth state of matter plasma. If you add more heat, more energy to a gas, you remove electrons from atoms and molecules, and you create a gas that's made of electrons, negative, ions, positive, and neutral atoms. And this is what we call a plasma. As our provost mentioned, dark matter aside, that's another debate, 99% of the known visible universe is in fact in the form of plasma. And the scales of the plasma are absolutely enormous. Galactic jets with sizes of hundreds of thousands of light years is a plasma. The sun is one big ball of plasma. The aurora is a plasma. Lightning is a plasma. And these are plasmas formed naturally in nature. Here on Earth, we have harnessed plasmas for technological purposes, for water purification, for plasma material processing, for making materials, for synthesizing materials, as surgical tools, and for electric propulsion. Plasmas is the hope for sustainability. We have researchers here at the University of Michigan working on fusion processes. This is where you use plasmas to combine atoms to release energy. And with that energy, you can produce green carbon-free electricity. And that's being studied in magnetic confinement fusion, inertial confinement fusion. And you take that green electricity and you convert bad chemicals into good chemicals through a process known as chemical conversion using plasmas. University of Michigan has an international reputation advancing the science and technology of plasmas in almost every field of plasma, from astrophysics to water treatment to laser-based accelerators. The Michigan Institute for Plasma Science and Engineering, MIPSE, works to enhance the impact of University of Michigan in plasma science and engineering. And in this presentation, I'd like to give you highlights of my colleagues' work and a little bit on my work of what we're trying to accomplish in these investigations. So let's start with a little bit of my work. As our provost mentioned, my work is in the area of low-temperature plasmas. And how does that work? Somewhere along the way, you create an electron appears, you take an electric field, you accelerate that electron to high speed, and that electron physically collides with an atom or molecule. And when that happens, you create an ion, but you also dissociate that molecule into chemically active species. Methane goes into methyl, oxygen molecules go into oxygen atoms. That is a plasma chemical process that creates a reactive environment that then you can make products and synthesize materials and modify materials, converting methane, for example, into methanol. One application of creating that reactive environment is semiconductor processing. Our lives revolve around microelectronics, cell phones, projectors, the internet, and that our lives are, the electronics are based on microelectronic devices, little pieces of silicon about a centimeter in size that have billions and billions of transistors fabricated in them. Each one of those transistors are only a few nanometers in size. A nanometer is a billionth of a meter. How you make that is in large part using plasmas. You start with a big wafer, you put it into a chamber, you sustain a plasma of reactive gases in contact with the wafer, and through etching and deposition processes, you make structures such as this. This is three-dimensional memory that's in all your memory sticks. Well, so our group develops computer models to describe those processes. We start with representations of the reactors. We predict the fluxes of these reactive species that come down onto the wafer. And then we have developed nanoscale molecular dynamics types of models that predict the evolution of the semiconductor devices under the bombardment of the wafer of these energetic fluxes. And these sorts of models are then put into a computer-aided design platform that are used by other colleagues, national laboratories, and industry. Speaking of microelectronics fabrication, we have on North Campus the Lurie Nanofabrication Facility. This is a world-renowned, state-of-the-art semiconductor device facility that is well known for the use by our faculty for developing quantum devices, biomems, microelectromechanical systems, microfluidics, labs on a chip, and neural implants. This is a wonderful facility that you can get a tour of to see how these things are actually made. But what you will find is that nearly all these processes involve plasmas. Plasmas remove material, they add material, they coat surfaces. Some examples of those plasma-aided processes that are performed in Lurie Nanofabrication Facility is work by Becky Peterson, who is also the director of Lurie Nanofabrication Facility, in which she uses plasmas to coat semiconductor devices with a single layer of atoms at a time. And she stacks these atoms of different types into three-dimensional structures to make advanced microelectronic devices. Zeishan Zhang, a new faculty member in ECE, uses those processes to make photonic devices. These are tiny little channels in semiconductors that are waveguides for light to make the communication between semiconductor devices much, much faster. And Zeishan uses plasma etching, a way to remove material from semiconductor devices to make his photonic channels. Perhaps the biggest legacy of LNF is its development of bio-MEMS systems, very, very small little factories, laboratories on a chip that are, again, fabricated using plasma techniques. This is some work by Sherman Fan in biomedical engineering, making little gas chromatographs on a little piece of silicon that's about a centimeter on the side using plasma processes. Yusik Yoon in the Department of Electrical and Computer Engineering makes biofluidic microchips in which, using plasma etching, makes very small channels that biofluids flow through that enables him to do drug screening, cell-to-cell interaction studies, and single-cell RNA sequencing. One aspect of plasmas is their ability to create reactive environments, to initiate chemistry. And one of the state-of-the-art applications of plasma is water purification. I think we're all familiar with the problems of contaminated water here in Michigan. And most of the techniques that are used to clean water, of PFAS, of mercury, of lead, of pharmaceuticals, are just adding other chemicals. And this turns out to be expensive and slow. But plasmas, being a very reactive system that you need only electricity to drive, are able to interact with water and remove those contaminants. John Foster in nuclear engineering, Alex Shuzeka in civil and environmental engineering are pioneering ways to apply plasmas in and around water to remove these contaminants. In that, John Foster has developed pilot systems which are designed to remove PFAS, the forever chemicals, from water that are now being tested out on a municipal scale. Another aspect of that chemical conversion is the ability to take bad things and turn them into good things. Take carbon dioxide, put it through a plasma, and convert that carbon dioxide to higher value chemicals. This is some work that's being developed by Joshua Jack in civil engineering, in which he's taking carbon dioxide and turning it into a feedstock chemical that's used in the chemistry industry. Herrick Clack in civil engineering is following a similar process of using plasmas in room air to activate species, and in this case is to kill viruses and aerosols. Though the COVID epidemic is not that far behind us, that we have forgotten that all those viruses were spread in aerosols. And Herrick has developed a technique in which you pull the air through these plasma devices and you can kill the viruses in the aerosols. His particular focus is in the agriculture industry, in poultry and dairy workers that have a much, much higher incidence of becoming sick by aerosol laden with viruses. Those types of plasmas that I have just discussed are what you might consider mild plasmas. They're not so energetic. At the other end of the extreme is what we call high energy density plasmas. We live in an environment of 1 atmosphere. At the bottom of the deepest trench in the deepest ocean is about 1,000 atmospheres. High energy density plasmas are energetic 1,000 times more than that, 1,000,000 atmospheres. And these are the sorts of plasmas that occur in astrophysical phenomena, like supernova and accretion disks in black holes, around black holes. They are also used for inertial confinement fusion to create green energy to produce electricity. And they're used in national security for stockpile stewardship. We have here at the University of Michigan 2 research centers funded by the Department of Energy with a focus on high energy density plasmas. The first is called CHEDR, the Center for High Energy Density Laboratory Astrophysics Research. The director is Carolyn Carantz in NERSC. And CHEDR is devoted to, in a laboratory setting, creating scalable plasmas that replicate the processes that occur, for example, in supernova. This is a fantastic area that, using big lasers, they make plasmas that are only a few millimeters across. But by using physics scaling laws, they can take that learning and apply it to galactic phenomena. The other center is called MACH. This is the Center for Magnetic Acceleration, Compression, and Heating. The director is Ryan McBride in nuclear engineering. This is a center that is studying the processes that will directly lead to fusion, taking plasmas to crush material to extremely high densities that will take atoms, put the atoms together, fuse them, and create even more energy. In that area of high plasma density, we have a brand new center funded by the National Science Foundation called ZEUS. This center is devoted to what's called high field science. This is using lasers to make very, very intense plasma that have extremely large electric fields. ZEUS is short for Zettawatt Equivalent Ultra Short Pulse Laser System. Only an engineer could come up with that acronym. But the end result is that this is the most powerful laser in the United States sitting on our North Campus. And the goal of this work is, I don't know how I can describe it other than magic, to take lasers that are so intense that when focused together, they create matter. They convert energy into matter, photons into electrons and positrons. Karl Krushelnik of Nuclear Engineering Department is the director of ZEUS. This is on North Campus. You're more than welcome to come and tour the facility. It's a fascinating facility filled with lasers. As we get off of planet Earth, we began to reach new applications of plasmas. One of the biggest reputations that University of Michigan has in plasmas is plasma propulsion. Once you get into space, you still need to move spacecraft. If they're in orbit, you need to keep them in orbit, or you want to send spacecraft to distant planets and to the asteroids. The most efficient way to do that is plasma propulsion. You create a plasma, charged particles, you apply an electric field, you accelerate those particles out the end of the spacecraft, and that produces thrust. And that thrust pushes the spacecraft to the distant planets. Here at the University of Michigan, we have a laboratory called PEPL, the Plasma Dynamics and Electric Propulsion Laboratory, whose director is Ben Jorns. PEPL has a 30-year reputation for pioneering developments in plasma propulsion. This is work that's done for NASA, for the Department of Energy, for Department of Defense, and for private industry. There is a vacuum chamber there that's about half the size of this room that you can actually walk into. It's very fascinating. And Ben's operation produces large plasma thrusters that will send astronauts to Mars and interplanetary missions, and small plasma thrusters for tiny little satellites called CubeSats. As we get a little bit further from Earth, we get to what's called space weather. Right? So the sun is a big ball of plasma. The sun pushes plasma, spews plasma out into the space between the sun and the Earth. That's called the solar wind. That solar wind of plasma gets to Earth and gets caught up in Earth's magnetic field. That produces the aurora, which is interesting. It produces chemistry in the upper atmosphere that we actually need, but it also can do bad things to our electrical systems on Earth. This whole system of charged particles going from the sun to the Earth and getting caught up in the magnetic field is called space weather. The Climate and Space Sciences and Engineering Department, CLASP, is the foremost institution in the world in development of simulations for space weather. They have developed what's known as the Space Weather Modeling Framework, which is the authoritative simulation for how things happen on the sun, travel through the space to the Earth, get to the Earth, and interact with the Earth. This is also applied to the planets. Most planets have magnetic fields, Jupiter, Saturn, and these sorts of simulations are applied to the interaction of the solar wind with the planets. The Space Weather Modeling Framework is used by the National Oceanic and Atmospheric Administration for predicting phenomena that may be damaging on Earth and then taking actions to prevent that damage. There are several faculty within CLASP who are principal investigators on NASA missions, developing instrumentation that goes out into the solar system to measure properties of the planets and the properties of plasmas around the planets. And we have on North Campus the Space Physics Research Laboratory, SPEARL, which is world-renowned for making instruments and making satellites and spacecraft that are sent to the distant planets. And Sue Lepre in CLASP is the director of SPEARL. Our faculty are not only excellent in their research, they're also excellent in the impact that they have on public policy. faculty and staff are active in national assessment of plasma science, leading to establishing policy and programs in federal agencies and industry. Some of the most recent reports that they've participated in are the Decadal Study of Plasma Science, sponsored by the National Academies, the Decadal Study on Space and Solar Physics, and the International Study on Petawatt Physics, the sorts of things that ZEUS does on North Campus. So let me leave you with an example of laser plasma interaction, some simulations done by Alec Thomas in the nuclear engineering department as an example of the excellent work and impact that our faculty have at University of Michigan in the area of plasma science and engineering. It's a vibrant interdisciplinary field that welcomes collaborations across campus. I thank you for your attention, and I welcome any questions you might have.
Thank you very much for your lecture, Professor. The paper is now open, or the lecture is now open for questions, and I believe we can also have an ability for those online to ask questions. There's microphones around. If you just raise your hand, we'll bring a microphone to you. Thank you. I'm happy to lead off with a first question, which is, as I was watching the low temperature part of your talk, it occurred to me that you seem to always make the plasmas and then use them immediately. And it made me wonder if you can actually store these plasmas, or is it of interest to store them? Or do they always have to just be made and used right away?
Well, their use is right away. But you bring up an interesting point that it is very difficult to store electricity. And that's one of the challenges of renewable energy, is that it's intermittent. The wind blows, the sun shines, but you may or may not need the electricity at that point. So you need to store that electricity. Storing that electricity in chemistry is one of the most efficient ways to do that. So you take the electricity, you do this chemical conversion, you make new chemicals of higher value, and then you put those chemicals in a pipeline, or you put it in a storage area, and you use them later. So plasmas is actually a way to store energy, not in terms of the electricity, but storing it in terms of the chemical bonds of the new materials that you make.
I see. And then after you produce the chemical, and then you can get the energy back through
Yes.
the plasma at the end.
Yes.
Thank you. Questions from our audience? Yes, there's one there.
Now, this is one of my students, so this is, I'm expecting the most eloquent question that you could ever imagine.
So as we're approaching the physical limit of plasma etching, how do you view the future of the semiconductor manufacturer, and then also how will plasma play a role in the future?
I did not prime him for this question. Plasmas are absolutely indispensable for semiconductor processing, and it will become even more so. And in fact, simulations are becoming the go-to tool in the semiconductor industry. You may have heard of the CHIPS Act that was enacted last year, putting huge amounts of money into the support of the semiconductor industry in the US. One important aspect of the CHIPS Act was to produce the digital twin for semiconductor manufacturing. You start with sand, the sand becomes a wafer, you go through 800, 900 manufacturing steps, and out comes a microprocessor. The goal is to represent that entire process digitally by computer simulation. Now, I wish this had started like 20 years ago, but there is just an absolute huge push to utilize fundamental calculations, surrogate model, artificial intelligence to optimize this whole process digitally. And plasmas will be an indispensable part of that.
And then we have a question in the back there. And a microphone is coming your way.
Could you say a little bit about the history of this work in the last 5, 10, even 20 years? What have been the big changes over the course of time?
Oh,
So the question was the changes in the field in the last 5, 10, and 20 years. How would you say that?
Well, one of the changes in the field just been the improvement in computations that allow you to do more. And on the experimental side, the diagnostics that have been developed over the last 20 years or so have been just utterly outstanding. In the old days, meaning like when I was in graduate school, most of the development of plasma devices was very empirical. You went into the laboratory, you really didn't know what was going on inside the plasma, and you just turned enough knobs and created enough parameterization that you finally optimized something. Over the past several decades, the ability to measure the inside of the plasma using lasers in particular has grown tremendously. So we're able to map all the intricacies of the inside of the plasma. And now, over the past several years, you take that huge amount of data and it goes into surrogate models and artificial intelligence that are then used to optimize the systems. And we simply didn't have that capability 20 years ago.
Thank you very much. Please join me in thanking our distinguished university professor.
Thank you, Professor Kushner. I really appreciate the interdisciplinarity of your work and the way you highlighted and elevated collaborators and experts on our campus. It was really great. I'm now pleased to introduce Dr. Robert Sellers, the James S. Jackson Distinguished University Professor of Psychology and Professor of Education. Professor Sellers is a world-renowned scholar whose contributions have transformed the discipline of psychology and the social sciences, earning recognition from the American Psychological Association as, quote, one of the most influential psychologists in the modern era. The major theme of his research examines the role of race in the psychological lives of African Americans, with particular focus on racial identity development and its influence on aspects of life ranging from academic achievement to mental well-being and physical health. His leadership as the university's first chief diversity officer led to the implementation of the U of M's first Diversity, Equity, and Inclusion Strategic Plan and the creation of the Wolverine Pathways program. He's been elected to the National Academy of Sciences and was selected to serve on President Biden's committee on the National Medal of Science. His work centers on providing evidence-based approaches to understanding and advancing diversity, equity, and inclusion in higher education. In this lecture, Dr. Sellers will share insights from his 32-year journey at the University of Michigan as a graduate student, faculty member, and administrator, highlighting both achievements and challenges in U of M's ongoing mission to provide access and opportunity while achieving academic excellence. Professor Sellers, the floor is yours.
Thank you, Lori. Good afternoon, everyone. Good afternoon, everyone. Thank you. I am deeply honored to be here and to accept this award induction honor, in particular, as it provides me an opportunity to address you today, as well as a really important opportunity to honor the person who I chose to name my Distinguished University Professorship after. And that's Dr. James S. Jackson. James, for those of you who don't know, was a giant, not only in numerous fields, but was a giant at the University of Michigan. And in many ways was a role model to me in terms of his tremendous contributions as a scholar. He was literally a Renaissance man across the social sciences. His impact in psychology, sociology, political science, public health, throughout the pretty much all of the social sciences and health sciences, James' work was important. And perhaps most important is his work emphasizing what at the time was still too novel of a concept, that black folks are worthy of being studied without comparisons to whites, that their actual existence, experiences were important in and of themselves, and redefining them as being important from a perspective of being human. He was also an incredible mentor, having mentored more students and early career scholars of color than anyone in the social, behavioral, and health sciences before him. And James was also a builder at the national level, but also a builder at Michigan. He was one of the founders of the program for research on Black America, was a tremendous leader as the director of the program for group dynamics, and an incredible leader as the director for the Institute for Social Research. So I'm deeply honored to be here. One of the first things I need to do before I continue my talk is to also acknowledge and thank my family, because without them, I would not be anywhere. And the fact of the matter is that I have been blessed over the years to have had tremendous parents, wonderful brothers and sisters throughout, as well as an extended family that has been nurturing and defining and supportive of me, including members who are Ohio State folks. We don't hold that against them. Even a dog has played an important role. But I also want to thank the person that's most important to me with regards to this journey, and that's my wonderful, beautiful, intelligent, inspiring wife, Tabby. Thank you, Tabby. The next thing I want to do is very, very briefly jump and talk very, very briefly about our scholarship. Basically, I have been blessed over the years to work with some tremendous scholars, and the nature of our work has really focused on the role of race in the psychological lives of African Americans. So our work is focused on racial identity, which basically means the extent to which individual African Americans define themselves in the context of race. Our work has been important, or at least has made a contribution with regards to noting the individual differences and variation with regards to those beliefs, and the fact that that individual variation in and of itself had important impacts for the life experiences of African Americans, and also that this work is important in other areas of their lives. Our work has also looked at racial socialization, recognizing that these attitudes about race don't come from anywhere, that there are processes particularly related to parents passing down what it actually means to be African American and how those messages play out. And then last but not least, our work has focused on the role of racial discrimination in the lives of African Americans. We've attempted to document the noxious and negative impact of experiences of discrimination in a variety of different forms have on African Americans, but doing so in a way that always recognizes the humanity of African Americans, recognizing their ability to cope, that they're not simply passive victims, but find ways as part of their struggle to incorporate racial discrimination. The third thing that I want to do in this talk is to also acknowledge my students. So all of that work that I just described very briefly really is a function of the hard work of some excellent, outstanding students, starting back in my early days at the University of Virginia, up to many of these different students over the years who have worked with me here at the University of Michigan. Many of those students, or actually I should say most of those students, have gone on to their own careers where they are mentoring a number of outstanding students themselves. they're making huge impacts within the field, and who I can honestly say without any humbleness that they have provided me with far more than anything that I have ever provided them. And so I'm deeply proud of their accomplishments. And now, the third part of my talk, and this is the talk that I think will encompass most of my message, and that's with regards to my experiences as a Chief Diversity Officer, but also across my experiences starting off as a graduate student back in 1985, all the way up through the past 27 years as a faculty member here at the university. And that's our effort to make the University of Michigan more diverse, more equitable, and more inclusive as a key strategy for us ultimately becoming excellent. This work has never been about me or simply me. It has been work that existed long before I ever got to the University of Michigan. These are my predecessors in the Chief Diversity Officer position. In the middle is Charles Moody, who was the very first person in my current role, or what was my role at the time, and then Lester Montz, who served in the role for 21 years. So that work has, the knowledge that this work is part of a larger effort had always been a part of the role of Chief Diversity Officer. And when I became Chief Diversity Officer, one of the things that I wanted to do was to try to create an opportunity for us as an institution to actually live up to our values. So one of the things I learned as a graduate student was that it seemed like much of the progress made at the University of Michigan had come from protest, oftentimes protest from students, sometimes protests from staff unions, et cetera. But the progress was always a contentious one. And yet at the end of that, we would always talk about and claim as an institution our values as being part of that. And one of the goals in developing the Diversity, Equity, and Inclusion Strategic Plan was to actually make that goal be part of the university's goal. That this would not be a contested activity, but instead would be something that we as an institution would take pride in and work towards and be proactive, so that we could get all the benefits of actually planning as opposed to negotiating social change and improvement. With that, you see the values that we wanted underneath these to empower voices that traditionally had not been a part of the process, to be inclusive as well as transparent in the work that we did, to make sure we built in accountability as an institution as we were moving forward, and last but not least, to institutionalize the change that we were attempting to do. And in this, and with the work of so many folks, we developed what was a very innovative, leading strategic plan, one that is viewed in higher education circles as literally leaders and best. Unfortunately, I'm here to tell you today that that plan, that effort, that DEI is currently under attack at the University of Michigan. From my perspective, the attack is capricious, specious. I couldn't think of another word that rhymes, so I jumped to based on more personal perspectives and not based on evidence. And unfortunately is damaging. And it's not only damaging and corrosive with regards to our efforts and progress with regards to diversity, equity, and inclusion, but because we recognize that diversity, equity, and inclusion is also the key to academic excellence, it is corrosive to our ability to consider ourselves leaders and best in that way. And it's particularly ironic and sad that this is happening given the fact that by just about any measure that is put forth, DEI at the U of M has been incredibly successful. It's been successful across a wide variety of constituencies at the University of Michigan and across the vast mission and structure and operations of this institution. Just to give you some examples, our work with respect to accessibility. Again, we've got work to do, but we've made tremendous progress, and that progress has been much a function of the university saying that diversity, equity, and inclusion and accessibility is important. You also see that progress and some of the work being done in things that you usually wouldn't think about with regards to DEI. Things such as far-reaching as enhancing supplier and investment diversity. Recognizing the huge economic power of this institution, are we utilizing that economic power in ways that are equitable and inclusive? And as a function of the DEI efforts, we began to look at this and began to develop plans to make these differences. And these are just two very, very small examples of the vastness of the work. It is also a fact that DEI is showing tangible evidence of progress. When I started off in the work, one of the critiques was, with regards to diversity, equity, and inclusion is, yes, it's a great feel-good kind of thing, but they never bring out evidence. Well, the fact of the matter is, we have all kinds of evidence. As a function from the beginning of our DEI efforts to now, we are much more affordable across the board. We've increased our affordability with respect to students. With respect to faculty, across a number of different measures, gender, race, also first gen, we see an increase with regards to our diversity in just about every area. Similar progress with regards to our staff, and progress with regards to our students. And it's important that you also note, including our first gen students. And these are just some of the measures. Now, in part of this argument, recent discussion has attempted to suggest DEI is not successful because it hasn't been successful with African American students. Now, I must say, I deeply care about where we are with regards to our progress with respect to African American students, and I was personally offended when those perceptions were thrown out there, particularly when they were thrown out in the context of individuals who have worked pretty hard not to increase our African American student population. So just for those of you who are wondering, we actually have more African American students at the University of Michigan than we ever had at any point in the history of the University of Michigan. And yet we still need more. In addition to those outcomes, DEI has also stimulated the creation of effective, important new programs. In other words, these outcomes didn't just happen, they were actually things that we did. Provost McCauley talked about the Wolverine Pathways program. Excellent program. Very proud of the work that it has done. LSA Collegiate Fellows Program, expanding our faculty and the diversity of our faculty, not just in terms of demographics, but in terms of the nature of the work that they've actually done. And in those processes, also made more equitable, diversifying the faculty recruitment processes that went into the Collegiate Fellows expansion. And those are, again, just two examples. And last but not least, it's really important that we understand it's not just programs. Because what happens sometimes is those who would like to shut down DEI will say, yes, we want to keep the programs, but it's the bureaucracy that is the problem. Well, first and foremost, those programs are run by people. So when you think of people as bureaucracy, those folks are actually run by people. But much of the success with regards to DEI goes beyond the actual processes themselves, or the actual programs themselves. I was blessed to have a tremendous group of folks, a team who worked with me in the provost office, in the Office of Diversity, Equity, and Inclusion. And just a small sample of the many different things that they did that are not necessarily tied to a specific program, but are fundamental to the University of Michigan, being the University of Michigan. And our diversity, equity, and inclusion efforts include everything from coordinating the DEI strategic plan techniques, which I argue are extremely important to our future and actually the key to our ability to address the challenges that we face today across a number of different constituencies, spending great time actually out there with the people, with the students, with the faculty, with the staff. Also coordinating our work with our implementation leads, who are out throughout the entire university, making the impact of DEI felt everywhere on our campus. So while our O-Day staff is important and fundamental, perhaps their biggest role is as force multipliers. It's their ability to connect people with other DEI leads across campus that makes a difference. To provide them with the kinds of professional development opportunities that allow them to be most effective in their jobs. And then perhaps most importantly, to create cross-unit collaborations that are very, very, very difficult in this institution to do without help and support. And last, I just want to throw this out there, given the New York Times piece suggesting that the university community did not feel that DEI has been particularly supportive. They quoted a difference between the 2016 survey and the 2021 survey in terms of general satisfaction, life satisfaction, and saw a dip between those two. Now, we know a lot of things happened between 2015 and 2021, and one's overall life satisfaction probably wasn't simply determinative with regards to DEI. But in that very same survey, which they had access to, in the very same data, when we asked a more specific question, specifically compared to the DEI climate at the start of the plan and now in 2021, how do you rate the current DEI climate? And you see significant differences with regards to an overwhelming, more positive rating of the DEI climate now than before. in which they attribute to the DEI process. And with regards to their satisfaction with the progress, again, even faculty, who as a faculty member, let's face it, we're not the most lovey, cuddly folks in the world. They even 2-to-1 report positivity there. But yet, that's not the story that we hear. That's not where we are. We are still at a place where there's a demand for DEI cuts without any actual argument for why. So we are at a crossroads here at U of M, and this crossroads really leads me to 3 questions that I'm going to leave you with. First, what's in a name? At a national level and here, we are spending a great deal of effort trying to change the name with respect to diversity, equity, and inclusion. Does that mean we're changing what we actually do? Are we changing our actual beliefs and our goals, our values, things that we have defined ourselves as being fundamental to us? Or are we just doing this to sort of get out of the way of the current political wave, which the current political wave has failed to define what DEI actually is? And anyone who is doing work related to DEI would be happy to define it for you and ask the question, well, is it the diversity you don't like? Is it the equity you don't like? Or is it the inclusion that we're no longer about? What is it that we need to change? So let's think about that in the name. I am as strategic as anyone. And it ultimately comes down to the work. But we as an institution of higher education have to ask ourselves, what are we actually doing? What are we actually doing? Second, as an institution, do we still strive to be leaders and best? I was very disappointed to read in the Daily yesterday, I think it was, a comment that suggested most of our effort is focused on trying to make sure that we right-size relative to our peer institutions. Is that really being leaders and best? Should we not be leading based on our values? Absolutely follow the law, which we have always done, which we continue to do. But we also have to follow who we are as an institution and not just some political whim. And then last but not least, and this is going to be a little personal, I need to know, where are you, President Ono? I'm sure this is not going to be well received, but the fact of the matter is, I have not heard any public word from you with regards to where you stand with respect to diversity, equity, and inclusion as a core value of the institution and where we're headed. And that article, if you haven't seen it, in the Daily, really looked like a person ducking and dodging, that suggested that he had nothing to do with any of this. And if that's the case, can you really call yourself a leader? I was disappointed to find out that you were the first president since the founding of the MLK Day ceremony to not show up. We've had presidents who have had pickets in front of their house, but yet still willing to show up at the convention because it was important to who we were as an institution. So I invite you, President Ono, to, like all of us, we can do better. And many of us are willing to help to work together to make the University of Michigan the place that we ultimately want it to be, the place that we love, the place that for 32 years, this man from Ohio was proud to say was a Wolverine. So with that, I want to say thank you, and I'm sorry that I blew through my time, Mike, for questions if that's the case, but thank you all, and I appreciate this honor today. Thank you.
Thank you very much. I think we do have time for some questions from the audience.
Okay.
If anybody would like to lead us off. Actually, this is often common. I'm happy to lead off with a question.
Oh.
And we're in the graduate school, and you did make a reference back to your graduate education days, and we're not exactly sure what you did as a graduate student. None of us were here, but it is a little bit legendary. I wanted to kind of just ask the question, given that you've given this talk, that you have experienced your professional career, is there something you would tell that graduate student that kind of experienced that model of activism changing the university, and then later you're promulgating this other model about how the university takes on that change project?
I would probably first say, yeah, you actually will be here 27 years, because as a graduate student, I thought as soon as I left Ann Arbor, I would probably never come back. Though I loved Ann Arbor, I thought I'd be someplace a little bit warmer.
But not all that time as a graduate student.
Right. I think the thing that I would tell that graduate student then was that there's so many people on this campus. There's so many people, faculty, definitely staff, administrators, who have similar cares with regards to the university and who, in their own right, are making a difference. And not to fall into the trap of assuming that what you see and perceive to be at the very top is their university. That it's actually your university and everybody else is there, which means you also have a responsibility to try to change it as well.
I think we have time for one more question from the audience. Lori, please. There's a microphone that will come to you.
Hey, Lori.
Is this on? Oh. I'm curious, you showed the photo of Lester Mons,
Yeah.
Charles Moody, and I'm just curious if you would reflect, the work that you're talking about is challenging. It always has been. And I'm wondering if you would compare challenges that Moody faced that we're still facing today.
So I was a graduate student, actually part of the protest that actually led to his position. So his position came as a function of student demands. And when he came into the position, there was this idea, well, he's at the time it was vice provost for minority affairs. And there was no office. There was no plan, because it was a negotiation, it was a demand, and nobody had any real sense of what this was going to be. And so he had to create and build an infrastructure to try to actually make a change and fight his way up to actually being recognized as a legitimate member of the university administration, and constantly building, fighting, building to be in that space. Lester will tell you this, benefited so much from it. But Lester came in, and people were telling Lester, well, you need to stay away from Moody, because Moody had to kick, scream, fight his way to get every little inch. And for the first year or two, he kind of stayed away because everyone said, oh, that Moody is just angry. He's just an angry black man. You're not going to get anything done in that case. And he realized the frustration, and what little bit he had came from Moody's fighting just to be in that space, and always saw it as an opportunity to build a little more, to build a little more, to build a little more. So when I got into the position, after 21 years of Lester's fighting, everything was laid out in terms of the university actually being in a place where we thought, okay, we have a chance to no longer be reactive, but we have a chance to actually live up to being leaders and best. And that being leaders and best isn't just meeting our moral obligation, and isn't simply about justice, which is a part of it, but that fundamentally to be the very best university we have to be, that we want to be. Diversity, equity, and inclusion has to be at the core of it. And it has to be at the core of the academic mission. It has to be at the core of the financial mission. It has to be at the core of what we do. And that's the only way that we actually have a chance to be leaders and best. And so for me, I was given a platform that they fought to get, that I had hoped, quite frankly, we were at a place to really just take off. But what has literally broken my heart is that we are about to undo much of that, and not because we weren't successful, or not because folks could tell us what they didn't like what we did, but because of people's own personal notions of what they think diversity, equity, and inclusion is, without actually knowing anything about diversity, equity, and inclusion, or their political aspirations to run, and that it is now politically expedient to be anti-DEI without being able to actually say what you mean by diversity, equity, and inclusion. And that's the part that literally is breaking my heart. If we had an argument, a conversation, an opportunity to sit down and figure out how we could do this the best, that would be a different story. And we were always willing to do that. And one last thing, and I'll shut up. What is also in that is we have gone back to a place where voices that are most important, that expertise that used to be valued is no longer valued. Is no longer valued. People who, by all accounts, are experts in what they do are somehow seen as being not objective. And yet people who have no idea are somehow seen as important. We would never do that in terms of if we had a medical crisis. We would never do that if we had a fiscal crisis. We would never do that in any other aspect of who we are as an institution. And so we as an institution are suffering. And we as an institution are in jeopardy of no longer being the institution that we were before. And that's above and beyond DA.
Thank you.
Thank you, Professor Sellers, for your passion and your commitment to our values. For our final lecture this evening, it's my pleasure to introduce Dr. Conwell Wang, the A. Gallup Olsoy Distinguished University Professor of Engineering, and the Stephen P. Timoshenko Collegiate Professor of Mechanical Engineering in the College of Engineering. Dr. Wang stands among the top mechanical engineering leaders of the century, recognized internationally for his pioneering work in structural dynamics and adaptive structures with embedded sensing, actuation, and control intelligence. The major theme of his research focuses on the development of adaptive structures and material systems, from functional materials-based structures to nature-inspired modular metastructures and mechano-intelligent systems. Professor Wang has created comprehensive models and methodologies that have been adopted globally, including groundbreaking work synthesizing piezoelectric circuitry concurrently with mechanical structures that have become standard practice in mechanical engineering. His innovations have been implemented by Ford Motor Company in millions of vehicles, enhancing performance and safety. He's published over 400 scholarly papers, given nearly 170 invited talks, and holds several patents. Professor Wang has received the highest honors in his field, including the ASME J.P. Den Hartog Award, the SPIE Smart Structures and Materials Lifetime Achievement Award, and the College of Engineering's Stephen S. Atwood Award. In this lecture, Dr. Wang will share insights from his research career, highlighting the evolution of his group's work from basic research to impactful applications in noise control, wave steering, and self-adaptive mechanical systems. Professor Wang, please.
Well, good afternoon, and thank you all for coming. And thank you, Provost Macaulay, for that very nice introduction. It is really my great honor to be here. Before I start my talk, I would like to first recognize the namesake of my professorship, Professor A. Gallup Oso. Gallup is the C.D. Moe Jr. Distinguished University Professor Emeritus and also the William Clay Ford Professor Emeritus at University of Michigan. He is a well-known scholar in the field of dynamic systems and controls. He has earned distinguished recognition from his peers for his impact and contribution solving critical dynamics and control problems, especially for manufacturing and automotive systems. He is a leader, a mentor, a friend, and a role model, not just to me, but to many others in the community. So I'm especially honored to be able to use his name in my professorship, and I'm very pleased to see both Gallup and his wife Susan in the audience. So Gallup and Susan, thank you for coming. Welcome. So the overall research interest of my group, the Structural Dynamics and Controls group, is to create methodologies for discovering, understanding, and realizing emerging mechanical structures. Our philosophy has always been to pursue basic research, building on the rigor of engineering science and mechanics, but at the same time, we're very keen on achieving technologies of practical importance. So today I would like to highlight a branch of our research that we've been pursuing for the last few decades in the field of adaptive structures and material systems. And this is a discipline that started about 35 years ago. The dream of the researchers at the time is to achieve adaptive structures with built-in sensing, actuation, decision-making, self-powered diagnostic and healing abilities, so we can adapt to changes in the environment and mission in real time. And here shows some of the journals and conferences in the discipline. And at that time, the researchers like to use this example to illustrate the ultimate adaptive structure. They use this T1000. I think some of you may remember T1000. It's from the Hollywood movie Terminator 2. I personally did not like this example because it's quite scary and dark. But on the other hand, it does capture all the major ingredient in that quote. So let's come back from science fiction to science. I can roughly categorize the research activities in my group into the following 3 categories in this field. They are namely responsive materials-based structures, nature-inspired modular metastructures, and embodying mechanical intelligence in structure dynamics. This is really an evolutional process for us. We really started from the left and gradually evolved to the right throughout the years as we're learning more knowledge and gaining new insight. On the other hand, all these 3 programs are very much coupled and intertwined with each other, and they're all under the umbrella of adaptive structures and material systems. So let's start with the first one, responsive material-based structures. The goal of this program is to embed these responsive active and reactive materials into structure design and to realize systems that can be adaptable. So here's an example that we pursued, is basically performing multi-field co-design and tailoring of these distributed and embedded piezoelectric materials concurrently with circuitry network in mechanical structures. Now, in terms of basic research, we have developed methodologies to synthesize these large-scale piezoelectric network so we can achieve structural vibration and precision controls. We have utilized nonlinearity and bifurcation to enhance sensitivity for structural sensing. And we created adaptable network for solving a very critical problem in structural health monitoring, which is the underdetermined, the inverse problem. So we can more effectively identify the location and severity of structure damage. And we harness nonlinearity and supertransmission to create non-traditional wave control for wave steering and energy harvesting. Now, due to time constraint, I will not go into the technical details of these projects, but if you're interested, we can always talk offline. So here shows some of my former students and postdocs who work on these projects. And in fact, they're the people who set up the foundation, the theoretical and experimental foundation of this program. As you see, some of them are already distinguished professors themselves at different institutions, and some of them are leaders in industry. So as I mentioned, on one hand, we're very keen on basic research. On the other hand, we're also very keen on developing technology from our research with practical importance. So for instance, through collaborating with Ford Motor Company, our system identification methodology were transferred to Ford, and through further development and implementation, now they're embedded in their millions of cars and trucks, enhancing safety and performance. And then through working with JPL, Jet Propulsion Lab, we have impacted their spaceborne remote sensing mission for Earth's climate study. And that is more specifically utilizing the piezoelectric network methodology we developed. We have been transferred that to them for surface control of their large space reflectors. And through working with helicopter company, we transfer some of our research to industry, help them develop rotorcraft vibration and stability mitigation devices and systems. So as we are seeing good success in harnessing these materials, functional materials into adaptive structures, we're also gradually evolving into new directions. And this takes us to the second program I mentioned, which is nature-inspired modular metastructures. And the overall theme of this program is to explore these adaptive metastructures based on modular architectures. That is, instead of designing structures directly from bulk material, we start from modules and trying to design, control, and integrate them synergistically. Now, this kind of architecture has often been observed in nature, such as biological systems. And here shows some of the research we pursued in this arena. They include like plant-inspired metastructures, earthworm-inspired metameric robot, and muscle-inspired metastable metastructures. Today, my focus will be on the first one, which is plant-inspired metastructures. And the goal of this project is to create a multifunctional adaptive structure concept through investigating the characteristic of plants. This is a fairly large program. It was funded by both National Science Foundation and DARPA, and it is a very multidisciplinary program. So we form a multidisciplinary team, and here shows our team with all the co-PIs at that time working with me. These include faculty and researchers with various backgrounds, including mechanical engineering, engineering science and materials, chemical engineering, biomedical engineering, and also people outside of engineering. So we have a couple of biologists on our team. So with these, we have explored new ideas inspired by the mechanical, chemical, and electrical property of plant cells. More specifically, we have created structures inspired by the fibular network configuration in plant cell walls, as well as achieving functions inspired by the nastic ion transport phenomena in plant cell membranes. So here shows some plant cells, and these cells consist of cell walls with microfiber embedded in them. When the cells are pressurized, they will deform, and the direction of deformation is a function of these fiber orientation. And these microscopic deformation of cells will translate into macroscopic movement of the plant, and this is the so-called nastic movement. And on the right-hand side, you see there's a movie clip of a mimosa plant. If you touch such a plant, it will deform drastically with large deformation and in a very fast manner. So inspired by these, we have explored two major ideas. The first idea is so-called fluidic flexible matrix composite, F²MC, and the second one is fluidic origami. And our focus today will be on fluidic origami. That is, we're trying to achieve adaptive structure inspired by the plant nastic feature together with the origami ancient folding art. And here shows a fluidic origami cell. Basically, we connect two of these Muri-Ori strips and form a chamber as shown on the right-hand side, and we apply these working fluid into the chamber. And as you see, this cell does not look exactly like a plant cell. However, it has the same key physical principle as the plant cell. For example, anisotropic deformation. As I mentioned in a plant cell, that comes from the fiber orientation. And in this cell, it comes from the origami folding or the folding angle. And as we apply these fluid pressure, we'll induce a volume change. And if we integrate many of these cells together, we can form a metastructure. And by applying pressure collectively, we can achieve various adaptive functions such as programmable multi-stability, fast snap-through, and shape morphing. And this, again, share the same physical principle as something we observed in the plant world, again, the Venus flytrap, as well as variable stiffness and energy absorption. So as we putting all these cells together and form modular metastructure, the interaction of these pressurized cells will provide us with very rich energy landscape and very multiple these tunable profiles. So by co-designing the origami parameters together with pressurization, we can program in different morphing shapes and stable state. In other words, we can reconfigure the origami lattice effectively. Now, by reconfiguring the origami lattice, we can achieve various engineering functions. And here shows one of them, which is an adaptive phononic structure for acoustic wave control. And in this case, we use the origami as a base, and we insert these cylinder inclusions on top of the origami. And then this becomes a metastructure. We put this in a host media, and the host media can be air or water, and we watch the acoustic wave going through this host media and going through this metastructure. And as you see here, as we're folding the origami from the left to the right, the lattice symmetry starts to change. And here shows the animation showing as we're continuously reconfiguring the origami, the lattice symmetry changed from hexagon continuously to square and back to hexagon. So these lattice reconfiguration not only can change symmetry, but also the so-called filling fraction. And from wave mechanics, we know these will change the wave propagation characteristic, and especially their band diagram. And here shows several very simple examples. We have rectangular lattice, square lattice, and hexagonal lattice. And as you see here, the band diagram is plotting the frequency versus the wave vector down here. And they show very different features of the band diagram when we change the lattice symmetry. And the red region is the so-called acoustic band gap or stop bands. Within these regions, the wave will be blocked. So with these basic principles, we have explored several case studies. The first one is so-called adaptive band gap engineering. Through both theoretical and experimental investigation, our outcome has shown that the origami metastructure can be morphed to effectively reconfigure the lattice and change the band gap. And here, the specific example I'm showing here, we fold the origami from 55 degree to 70 degree. We see we change the band gap drastically. The band gap are denoted by the color region, going from 3,000, 4,000 hertz to 6,000 to 8,000 hertz. And again, the band gap are the regions that the wave, the acoustic wave, are being blocked or the noise are being blocked. So harnessing these basic research outcomes, we are, together with our licensed patent, we are working with industry to develop these more scale-up sonic barrier technologies so we can block noise at all times, even when the noise is changing frequency. We're hoping to reduce the noise pollution in the environment, such as traffic noise. The second case study is on beamforming and wave steering. In this case, again, we're changing the lattice symmetry. Not only will affect the band diagram, we also affect the so-called direct points, and it's shown on the right. These direct points are the intersection of these frequency branches in the band diagram. And by definition, that will change the beamforming and wave steering frequency and directions. And here shows an example. We have two cases. Basically, we fold the origami from 84 degree to 75 degree. We switch the direct point from A to B, and we basically reconfigure the lattice from a square lattice to a rectangular lattice. And we place this in a chamber. Left-hand side shows a line source of the acoustic noise. And then it goes through this metastructure. On the right, we see the beam formed and has a steering angle, and it changed drastically as we fold the origami. It goes from 0 degree to 64 degree. And that tells us that is folding the origami can steer the wave, covering a very wide range of directions, and that could be useful for us to develop acoustic remote sensing devices. So now this takes us to our third program, which is on embodying mechanical intelligence in structural dynamics. This is a fairly new program for us, not just for us, for the whole community, in fact. And this is our vision for the future of the field. And as we know, in recent years, there's tremendous societal needs and advances in autonomous systems. And these include human-centric robots, smart wearables, automated vehicles, and intelligent infrastructures. And because of that, there's greater and greater demand for the next generation of adaptive structures to be even more intelligent. And people recognize that these structures will be much more effective, efficient, and secure if some of the intelligence can be outsourced and embodied in the mechanical domain. Versus traditionally, we usually code all the intelligence into a centralized digital computer or microprocessor. Now, this is analogous to another phenomenon we observe in the nature, which is the octopus. As we know that octopus, their so-called brain power and neurons are not centralized in their head area. In fact, they're well distributed through their 8 arms for decentralized mobility control. So that's the spirit of mechanical intelligence. That is, we want to develop intelligence in the design of the mechanical system. So our system can be in synergy with, but rely less on the conventional platforms built solely on add-on electronics and digital computers. And Our system could be more energy efficient and sustainable, has more direct interaction with the surroundings, and is much more resilient against harsh environment and, very importantly, cyber attacks. So this kind of concept, although new, has been very intriguing, and there are studies already being attempted to achieve macro intelligence, and there are some very smart design and promising results out there, but many of these designs are still very ad hoc and has very narrowly defined functions. So there's still lack of a systematic foundation for us to construct and integrate the different elements of intelligence, such as perception, that is perceiving information from sensory input, memorizing the information, making decisions, and commanding outputs. So our vision is to advance the state of the art of mechanical intelligence by harnessing the so-called physical computing in the mechanical domain as the needed foundation for us to integrate these essential elements of intelligence at the system level. So to do that, we have developed several test beds to test out our idea and our hypothesis. This is one of them. It is a self-tuning phonetic structure for elastic wave control. We want the structure to perceive different inputs and make decisions to reconfigure itself and control its own wave characteristics. On the left-hand side shows a schematic of our test bed and also a photo of the experimental setup. On the right-hand side shows a state space representation of our test bed. So in a nutshell, what we want to do is to harness the structure, the dynamics of the structure as the reservoir for physical reservoir computing. In other words, we're treating the mechanical structure as a physical neural network or mechanical neural network, so we can train this mechanical neural network through machine learning and actually achieve intelligence. In other words, we want to directly embody the neurons and the so-called brain power within the functional mechanical body, just like the octopus. So here I just want to show you some results from our test bed. This is a frequency selective structure for vibration isolation. In other words, we want this to be an intelligent barrier to isolate vibration under changing excitation frequency. On the left-hand side shows the band diagram with all the training data, testing data, and target data. And for this example, we excite the structure at 134 Hertz. On the right-hand side shows experimental testing performance result. We're plotting the vibration amplitude as time goes on. So the blue line is the input excitation, and the red line is the vibration at the output. As you see, before the reconfiguration, the red line has very large amplitude. That means we have large vibration level. And after reconfiguration, we see the red line amplitude become very, very much suppressed. So this tells us this metastructure can perceive input excitation frequency and reconfigure itself to block or isolate the vibration. So these are very successful outcome in the one-dimensional structure. So we got encouraged. We start to look into higher dimensional. This includes two-dimensional, three-dimensional, and fractal structure. We're especially interested in harnessing these higher dimensional topological physics for wave-based computing. Especially in this case, we can create these protective waveguides that are insensitive to defects or uncertainties in the materials, so we can transfer signals in a very robust manner and create logic gates and memories to advance the computing. So this takes us to our ongoing work. So we have success in these component level, element level. We are pulling all these knowledge now together and trying to attack a more integrated complex system problem. And this is a large-scale project funded by, again, National Science Foundation and DoD, and where we have collaborators at Michigan as well as Virginia Tech and Penn State. And we're excited about this opportunity because it will help us answer some of the very fundamental and challenging research questions. And we're hoping to move the needle and elevate the field to the next level. So now let me conclude my talk by saying thank you to many, many, many people. I want to thank my students and postdoc and sponsors. My students and postdocs are the people who did all the work I presented today. They're sitting in the back. And being a professor, it is really my deepest joy and my greatest privilege to be able to work with so many outstanding people. I want to thank my colleagues and peers, especially people at University of Michigan, especially in Mechanical Engineering Department, but also across the community. Some of them are my collaborators, my friends, my mentors, and my mentees. They kept me honest, they kept me going. And finally, last but definitely not least, I owed everything to my family. They were with me throughout my journey with all their love and their strongest support. And I consider myself a very lucky person, and I'm truly grateful. With that, I finish my talk. Thank you.
Thank you. Questions for our distinguished university professor? Yes, there's a question there. Thank you.
Oh.
Very nice talk. So we talk about the dream, and we always talked about adaptive, smart, intelligent, and we've always been able to do adaptive. We've always struggled with what smart meant, and intelligent always was kind of the dream, right, of how do we get there. You've shown a lot of different things and the progression that you've had of how we get more intelligent. Now with AI coming along, how can we leverage that to actually make intelligence that can learn and not only adapt but learn from things, and how can you work that into your mechanical?
In fact, the mechanical intelligence, the AI and machine learning is part of it. That's because the whole thing is about using the mechanical structure as, quote unquote, the mechanical physical computing device. And the whole thing we're doing here is treat it as a physical and mechanical neural network. And definitely the training and the AI is part of it. So this is a great topic. In fact, the mechanical intelligence was recently, there's an NSF workshop on this topic, and I happened to attend. Okay, so the first thing they do is they say, define intelligence. That takes 2 hours, and there's no conclusion, okay? And we're only just engineers. Even engineers talking, we cannot conclude what is intelligence. So we decided to give up that. And the things we're doing here is it's a little bit easier. We define things as intelligence, basically the things we coded in our computer today, no matter which control algorithm you're using, but using digitized things or digital media to do that. And we're trying to translate some of those into the mechanical domain. So we get away from the discussion of what is intelligence. Is learning part of it? Can mechanical system really learn? I think that's still a big discussion, and I think the report is coming out, and I can send that link to you when the report comes out. Okay, so that's definitely a good discussion among the community.
So I'm going to focus on one bit of what you were talking about, about bio-inspired design. And we all like doing that, and it's fun, and you can come up with really creative solutions. But what I'm really asking about is how limiting is bio-inspired stuff? Because there's some very famous engineering structures that don't appear in biological systems, like the wheel, for example.
Yeah, great question. In fact, when people give bio-inspired design or control or structures, I always ask similar question you ask. I said, do you really need to be inspired by biology or nature to do that? I think in general, learning from nature, from biology is the right thing. We should be humbled because nature has been around for a long time because of evolution. But on the other hand, we have to be also very careful, because what nature does sometimes is not what we want to achieve. Sometimes we build machines to be faster, stronger, performance-oriented. But if you look at what some of these structures or the nature, what they do is they are not really shooting for performance. Sometimes they're looking at longevity, they're looking at sustainability. So the quick answer is yes, we should learn from nature. However, we should be selective. We should know why nature go that way. Instead of saying, oh, nature did that, must be good. So if I learn from them, I build something, it'll be faster. No, nature may not want to be fast. Nature want to live longer, for example. So that's a great question. I always have that debate among myself and my colleagues and my students.
Thank you. Please join me in thanking our distinguished university professor.
Thank you. I didn't get a question from my student.
That concludes our session. Thank you for joining us today. On behalf of Provost Macaulay and myself, please join us for a reception that is right across the hall. Thank you very much.